Welcome friend. Again we have to discuss the calculus. First, in the previous lecture we discussed monotone sequence and some example on the monotone sequence. So what is monotone sequence? Monotone, it is either increasing or decreasing, and we see that time that is the monotone Conogen theorem. So what is monotone Conogen theorem? If the sequence is monotone and it is bounded, then we say that it is a convergent. That is, if the sequence is increasing and it is bounded above, then we say that this sequence is convergent. Or we can write, if the sequence is decreasing and it is bounded below, then we can say that this sequence is convergent. In the today's lecture we have to discuss the subsequence and some theorems on subsequences. So we start our today's topic, that is the subsequences. So first we write the definition for the subsequences and we take some examples. So our topic is subsequences. What is sequences? What is sequence? Sequence is a function from n to the set. That is, sequence is a function. So we have to write the sequence, and for this we have to consider one sequence, and then we write the definition for the subsequence. So how we write the definition? Definition of subsequence. Definition first we write x is equal to xn is a sequence of real numbers and n1 is less than, n2 is less than, and so on, nk is less than dot dot, is a strictly increasing sequence of which numbers? Natural numbers. Okay, so we consider one sequence, and then what we are taking here, that is n1 is less than, n2 is less than dot dot, nk is less than dot dot. Okay, it is a strictly increasing sequence of a natural number. Then the sequence, which sequence? X dash. Then the sequence x dash is equal to x and k is called a subsequence of x and is given by x1, xn1, xn2, xn3 and dot dot, xnk and dot dot. We can write like this. That is, if there is a strictly increasing sequence of natural number n1 less than, n2 less than, nk, then there is a sequence, that is x dash is equal to x and k. It is called as the subsequence of x and is given by xn1, xn2, xn3 and so on. This, for example, we take x is equal to 1 0 1 0 1 0 and dot dot. Then what we can write here? Then what we can write? X dash is equal to what? 1 1 1 1 and dot dot. And what we can write? X double dash, it is equal to 0 0 0 0. This is the subsequence. Then x dash and x double dash are subsequences of sequence x. How it is? Suppose this is our n1 this is n2, n3, n4, and is it? Then what is it? This is nothing but xn1. Is it? This is our xn1. This is our xn2, and so on. We can write here also. You can write xn3 here. Okay, xn3, and so on. You can write like this. But no need to write these things. No need to write these things. So what we are getting here? Sequences. And one more example we can write here. That is, suppose x is equal to what we are taking? 1 upon 1, 1 upon 2, 1 upon 3, 1 upon 4, 1 upon 5, and so on. Then what we can write? X dash is equal to 1, 1 by 3, 1 by 5, and dot dot. It is what? Odd number of sequence or even number, so it is 2n minus 1, and dot dot. And what we can write here? X double dash is equal to, it is equal to, we can write the even number sequence also here. That is the reciprocal of even number sequence. How we write? We write 1 upon 2, 1 upon 4, 1 upon 5, and dot dot. It is how much we can, how we can write this? How we write this? 2n are the subsequences of x is equal to 1 upon n. We can write this sequence as x is equal to 1 upon n. So in the similar way we can find subsequences of a given sequence. Okay, so we will go for the one theorem. Okay, so we will go for the theorem. So what is theorem statement is given? If a sequence x is equal to xn of real numbers, this converges to x. That means what is given? We have a one sequence of real number, and this sequence is converges to the x. And what it means? What it means? This converges to x means its limit is x. Its limit is x. Its limit is x, then you can find the, or you can write the definition, epsilon delta definition of this. So this is your given, and what we have to prove? Then any subsequence of x also converges to the x. Then what you have to prove? Then it has a one subsequence x and k. This subsequence is also converges to the same limit, that is x. So we will try to prove this. So what is given? Given x is equal to xn is converges to x. Converges means what? Limit n tends to infinity of xn is equal to what? It is equal to x. And it is equal to x means what? By the definition. By definition of limit. What we can write by the definition of limit? For every epsilon greater than 0, there exists a natural number k, capital K belongs to the n, such that what we can say? Such that mod of xn minus x is less than, it is less than epsilon for all n is greater than or equal to k. For all n is greater than or equal to k, we can say. Okay. Okay, so this is our first statement, you can say. Okay. Then what we have to prove? The subsequence x and k converges to the x. That means we have to replace this xn by x and k. How we replace? For this what we have to given? So what we can write? We have n1 is less than n2 is less than n3 and dot dot nk is less than is a strictly increasing sequence of Which numbers it is? Natural numbers. Natural numbers. This is the sequence of a natural number, strictly increasing sequence of a natural number. Hence by induction we can prove what we can prove this nk, or we can prove nk is greater than k. Nk is greater than k. Okay, this by induction we can prove this. If this is small k, this is a small k, we can write it is a small k. Okay, so what we can write here, if small k is greater than or equal to capital K, then what we can write? Then we can write this xn minus x is less than epsilon for all what? For all what? And here you can write this nk is greater than k is greater than or equal to capital K. Okay, then it is greater than or equal to capital K. This is greater than or equal to, this is our capital K, and therefore this is what? From first, and therefore we can say that therefore the sequence x dash is equal to x and k is converges to x. This is very simple theorem. So what we did, just we write a definition, then we take a support of this strictly increasing sequence, and by induction we can prove nk is greater than k, is it? And this k is greater than or equal to, if this k, small k, is greater than or equal to this capital K, then we can write nk is greater than k is greater than or equal to capital K, and therefore from first we can write this, and therefore the sequence x dash is equal to x and k is converges to x. Okay, so in the similar way we can prove one more theorem now. Okay, so we prove now second theorem. So what is the statement of second theorem? Suppose x is equal to xn with the sequence of real numbers. So we have given one sequence of real numbers, and then the following statements are equivalent. Then what we can write? The subsequence x is equal to, or the sequence x is equal to xn does not converge to x belongs to the R. That is the real number x. It is not convergent is given, that means it has no limit x. Okay, then there exists a epsilon greater than 0 such that for any k belongs to the n, there exists a nk belongs to n such that nk is greater than or equal to k, and mod of x nk minus x is greater than epsilon 0. Then one more thing, that is there exists an epsilon 0 and a subsequence x dash is equal to x n k of x such that x n k minus x is greater than or equal to epsilon for all k belongs to the n. For all k belongs to the n. So how we write proof? We have to prove A implies B implies C, and then C implies A. Then we have to prove A implies B. So first we prove A implies B. First we prove A implies B. So what is the statement is given? What is the first statement given? What is given? The sequence x is equal to xn is or does not converges to x, real number x. Therefore what we can write? Therefore for every epsilon 0 greater than 0, there exists a natural number, or we can say there does not exist a natural number k belongs to the n such such that what, or we are not able to find a natural number k such that what, mod of xn minus x is less than epsilon for all k is what, n is greater than or equal to k. That is what, in other words, what we can write, we are not able to find k belongs to the n. That means what, there exists a k such that this here should be epsilon, this must be greater than or equal to, this must be greater than or equal to epsilon. That means, in other word, for every epsilon 0 greater than 0, there exists natural number k belongs to the n such that what, such that mod of xn minus x is greater than or equal to epsilon 0 for all n is greater than or equal to k. And that means what we can say, that by the above theorem, or we have n1 is less than, n2 is less than, and so on, nk is less than nk plus 1 and so on, is an strictly increasing sequence of real numbers. This is the sequence of real numbers. Then we can prove by induction. We write it is in the first theorem. Similar statement we have proved, that is nk is greater than or equal to k. Okay, then if here our k is greater than or equal to capital K, then what we can write? Then we can write nk is greater than, k is greater than or equal to our capital K. Then we get what we are getting from this, for every epsilon 0 greater than 0, there exists nk belongs to the natural number, or there exists k belongs to the n such that what we can write, xnk minus x is less than, or it is greater than or equal to epsilon 0 for all nk is greater than or equal to k. For all nk is greater than or equal to k. That means here we are able to find the nk such that what, this mod xn minus xnk minus x is greater than or equal to epsilon 0. Now we prove part second, that is B implies C. Here what we prove, part first, that is A implies B. Now we have to prove part second. And what is given in the part second? Given that there exists epsilon 0 greater than 0 such that what, for any k belongs to the natural number, there exists nk belongs to the n such that what we can write, mod of xnk minus x is greater than or equal to epsilon 0 for all nk is greater than or equal to k. This is you have given. And so now what we can write here? Now what we can write, let epsilon 0 b is in given. Now what we can write, let n1 belongs to the n such that what we can write, n1 belongs to the n, n1 greater than or equal to, n1 is greater than or equal to 1, and what we can write here, mod of x n1 minus x is greater than or equal to epsilon 0. Similarly, what we can write, let n2 belongs to the n such that what we can write, n2 is greater than or equal to n1, and what, mod of xn2 minus x is greater than or equal to epsilon 0. And similarly or continuing in this way, what we are getting continuing in this way, we get a sequence x dash is equal to xn1, xn2 and so on, xnk and dot dot, such that what we can write here, mod of what, xnk minus x is greater than or equal to epsilon 0 for all n is greater than or equal to, for all k is greater than or equal to k belongs to the n, for all k belongs to the n, and we are getting our third statement. So what we did, just we take n1 such that this holds, n2 such that this holds, continuing in this way we are getting our subsequence x and k which holds the given equation. Now what we have to prove? Now we have to prove the part third. And what is part third? C implies A. We have to prove now C implies A. So we go for the part 3. Okay, so what is part 3? We have to prove C implies A. So what is given in the C part? That is, there exists an epsilon 0 greater than 0 such that subsequence x and k of x such that x and k minus x is greater than or equal to 0. From the part C, we say the sequence x is equal to xn is not convergent to x if, yes, that is, if x is equal to xn is convergent to x, then by above theorem what we can say, by above theorem the subsequence is convergent, or it is convergent to x, and then what we can do, epsilon 0 greater than 0, what we can write, there exist n belongs to the, or k belongs to the n such that mod of x and k minus x is greater than or equal to epsilon 0 for all n is greater than or equal to k, and which is contradiction to our given statement, which is contradiction to given. Hence what we can write, x is equal to xn must not converges to x. Okay, It is not convergence. If it is convergent, then this inequality holds for all what n greater than or equal to k, but it is holds for all k belongs to the n. There is not a any condition. In the similar way, we can prove so many theorems on this. Just try to understand the statement of the theorem and try to write the given and what we have to prove. You will get the idea of the theorem. So today we will stop here. Thank you very much.